Welcome to this explainer, where we're going to break down the exact skeleton you need to absolutely conquer your system design interviews. Today, we're tackling a classic: design a rate limiter. Now, this specific challenge is fantastic because it's actually small enough to fully finish in a standard 45-minute interview, yet it perfectly teaches you the exact framework you're going to reuse for almost any other system design problem they throw at you. We'll figure out how to clarify requirements, estimate scale, design the API, pick a core algorithm, and finally take the whole thing distributed. Let's get right into it.
Okay, so first things first, we need to establish the golden rule of system design interviews. Never, ever jump straight to a solution. Instead, you've got to open with clarifying questions. A rate limiter can mean 5 completely different things depending on the context, so you need to narrow it down out loud. Ask them, are we limiting requests per user, per IP, or per API key? By simply asking whether this is a client-side limiter versus a server-side one, you instantly prove to the interviewer that you've built real systems, because in practice, those are wildly different problems. For our explainer today, let's assume the interviewer responds that it's a service-side limiter, sitting right in front of our API, limiting requests per user, and crucially, it needs to work across multiple servers.
To tackle this, we're going to follow a very specific step-by-step playbook. 1. Setting up for success. 2. Choosing the core algorithm. 3. The single server design. 4. Going distributed. And 5. Optimizations and wrap-up.
Starting with step 1. Setting up for success by clarifying constraints and estimating scale.
Before you even think about writing a line of code, we have to categorize our requirements. On the functional side, obviously we need to limit requests, let's say 100 per minute, and reject any excess traffic with an HTTP 429 too many requests status. We might also want to support different rules for free versus paid user tiers. But I really want you to notice the high availability requirement on the non-functional side. Specifically, the idea of failing open. This is a massive real-world design decision. It means that if our rate limiter crashes, we would much rather let all the traffic through than accidentally block legitimate traffic and take down our entire API. Stating this explicitly early on is exactly the kind of engineering judgment that interviewers desperately want to hear. Plus, calling out that eventual consistency is okay, meaning we can afford to be off by a few requests during a split-second race condition, makes this whole problem so much more tractable.
Next up, we need a quick back-of-the-envelope estimation to ground our whole design. Let's say we have 10 million daily active users, and they each average about 10 requests a day. Doing the math, that gives us an average of roughly 1,150 queries per second. If we account for, say, a 5x traffic spike during peak hours, we hit a peak of 5,750 queries per second. Now, while 5,750 QPS isn't a massive number for a modern backend system, you have to remember that this rate-limiting check must happen on every single one of those requests. That number proves our check has to be incredibly cheap. We absolutely cannot afford to reach for heavyweight, slow consistency mechanisms like distributed locks on every single API call.
Moving into section 2, choosing the core algorithm. Let's run a little elimination tournament.
This right here is the heart of the interview. Honestly, seeing how you walk through algorithm trade-offs out loud is what truly separates a strong candidate from someone who just memorized a textbook answer. So, we run an elimination tournament. First up, the fixed window counter. It basically divides time into fixed windows and increments a counter. Sounds great, right? It's dead simple, uses very little memory. But it has a fatal flaw, the burst problem. If our limit is 100 requests per minute, a malicious user could send 100 requests at exactly 12:01:05 and then another 100 requests right at 12:01:01. They just pushed 200 requests in 2 seconds, completely bypassing our intended rate. So that one's out. Next, we consider the sliding window log. This one stores a timestamp for every single request. It is perfectly accurate because it drops old timestamps dynamically. But we have to reject it too. Why? Because storing a timestamp for every request, for every single user, means our memory usage is going to grow continuously with request volume, and that is just far too expensive at our scale.
So comparing our remaining options, we look at the sliding window counter. This one uses a weighted average of the current and previous fixed windows. It's actually a really great practical middle ground. It gives us fixed window memory costs while smoothing out the traffic with just a slight, totally acceptable approximation error. But it's time to crown our ultimate tournament winner, the token bucket algorithm. It handles short bursts beautifully, it is incredibly cheap on memory, and it perfectly matches real-world traffic patterns, even if the underlying logic is a tiny bit more complex. And you know, the token bucket isn't just computer science theory, it is the absolute industry standard. It's exactly what massive production systems like AWS and Stripe actually use under the hood. The concept is super intuitive. Imagine you have a bucket with a set capacity. Tokens refill continuously into that bucket at a fixed rate. Every incoming request takes one token. If the bucket is empty, the request gets rejected. Boom. When you're in the interview, confidently state that you'd go with the token bucket for these exact real-world reasons.
All right, step 3, the single server design. Let's figure out how to build the local logic.
With our API designed as middleware, meaning it sits right at the top of the request handling pipeline, running before any heavy business logic, the underlying code is remarkably elegant. We'd keep an in-memory hash map linking a user ID to a token count and a last refill timestamp. On every single request, it's just a simple 3-step process. Step 1. Compute how many tokens to add based on the time that has passed since their last refill. Step 2. Cap that total so it never exceeds the bucket's maximum capacity. Step 3. Check those tokens. If you have at least one, decrement the count and let the request through. Otherwise, reject it. This is wildly efficient because at the end of the day, we are only tracking 2 numbers per user.
Next is Section 4, going distributed. This is where we scale to real-world chaos. Because let's be honest, designing for a single server is way too easy, and a good interviewer will inevitably push you to scale. Moving to multiple servers completely shatters that nice local memory design we just built. Think about it. What actually happens if a single user's traffic is distributed across 3 different servers sitting behind a load balancer? If we rely solely on local memory, Server A, Server B, and Server C all have their own isolated token buckets for that exact same user. That means the user is effectively getting 3 times their allowed limit. This right here brings us to the most critical pivot in our entire system design. To fix this, we have to pull the state completely out of the individual servers. We're going to centralize our counter state using Redis, storing each user's bucket as a Redis hash key. But wait, this introduces a classic race condition. If 2 servers try to read and write to that exact same Redis key concurrently, they might both allow a request that should have been rejected. The professional, bulletproof way to solve this is to use a Lua script. Redis guarantees that a Lua script executes as a single atomic operation. This means our entire refill and decrement logic happens completely inside Redis in one go, entirely eliminating that round-trip race condition. Finally, at our 5750 peak QPS, a single Redis instance is totally fine, but we would absolutely make sure to co-locate the Redis cluster in the exact same region as our app servers to minimize any network latency.
But what happens if Redis just crashes? Remembering our non-functional requirements from the very beginning of the interview, you must explicitly tell the panel what your strategy is here, and that strategy is that you will fail open. If the centralized Redis cache suddenly becomes unreachable, your middleware should just let the request through rather than blocking everything. Rate limiting is there to protect against abuse, sure, but a rate limiter outage should never, ever cause a total system outage. Prioritizing your core API's availability over strict limit enforcement is a massive green flag for any engineering interviewer.
Finally, Section 5, optimizations and wrap-up. Let's nail that final impression. So we've successfully built a robust distributed system. But as the interview clock starts winding down, having a few rapid-fire optimizations in your back pocket will absolutely secure you top marks. You can easily impress the panel by suggesting a hybrid approach for extremely high-traffic situations. This means keeping a short-lived, local approximate counter on the app server that just periodically syncs to Redis, basically trading a tiny bit of accuracy for blazing fast speed. You can also suggest data-driven tiers, where you store user tier limits in a database, allowing product managers to change rate limits on the fly without requiring a full code deployment. Or you could even mention multi-dimensional limits, where you leverage this exact same token bucket primitive to run IP, user ID, and API key limits all at the exact same time. When the interviewer inevitably asks you to summarize your final design, you want to hit every single major architectural beat. Confidently state that you'd implement a token bucket algorithm backed by Redis for shared state across multiple servers. Call out that the logic would be done atomically via a Lua script, that you'd intentionally fail open if Redis becomes unavailable, and that you'd shard Redis by user ID if you eventually outgrew a single instance. Delivering a summary like this is your mic drop moment. It demonstrates total mastery over the entire problem space.
And just like that, we've successfully built a rock-solid foundation for system design by conquering the rate limiter. You now know exactly how to handle hash maps, distributed caches, and race conditions at scale. But the real challenge moving forward is whether you can take these exact mental models and apply them to entirely different architectural monsters down the road. For instance, how would you pivot these new skills to tackle the unique, incredibly read-heavy base-62 infrastructure required to build a massive URL shortener? Think about how your engineering instincts would have to shift for a system heavily reliant on generation and retrieval. Keep that in mind, because we will be exploring exactly that puzzle next time.